just pull a random page from the phone book, one step, and say, here it is. But that's not necessarily going to be accurate unless I get really, really lucky. So the graph really only speaks to efficiency and the design of the algorithm, not the correctness of it. To analyze the correctness, you need to use another mechanism altogether, namely logic. Other questions now on efficiency in this way? No? All right, so with that in mind, let's begin to translate this to some actual code. And in fact, before we look today at one actual programming language, albeit a graphical one, let's consider something called pseudocode. So pseudocode has no formal meaning. Generally, you write it in English or whatever your own human language is, but you write your thoughts down tersely, succinctly, but precisely. You try to really convey your thoughts, not with a wave of the hand metaphorically, but step by step, precisely. So what do I mean by this? Here might be some representative pseudocode via which I describe that third and final algorithm in a way that I could hand it to you, and you could do the same at home. Or I could hand it to someone at Google, and they could implement it in Android. Or I could hand it to someone at Apple, and they could implement it in iOS. So step 1, I claim, was pick up phone book. Step 2 was open to the middle of the phone book. Step 3, look at the page, as I did. And now things get a little more interesting. Step 4, if person is on page, I have to make a decision. Presumably, what should I do if John Harvard is on the page I'm looking at? So stop and probably make the call or email or whatever the goal might be. And so I'm going to actually indent this visually by a few spaces just to make clear that you should only do line 5 if the answer to line 4 is yes. Otherwise, you don't bother. The next thing I'm going to do, line 6, is consider another possibility. If the person I'm looking for is earlier in the book, what do I want to do? Well, I could describe this in a bunch of ways. I'm going to do this tersely as follows. Open to the middle of the left half of the book. So to open to the middle of the left half of the book. And then what am I going to do? Well, I've just kind of divided the problem into something smaller, but it's fundamentally the same problem. It's just a fewer number of pages. So I'm just going to go back to line 3 and do it again, because the problem's just getting smaller and smaller, presumably. Else, if the person I'm looking for is later in the book, open to the middle of the right half of the book, and also go back to line 3. But there's a fourth possibility, and it's failure to realize sometimes that there's other possible outcomes that make computers crash or spinning beach balls or the like if a programmer doesn't anticipate some situation. What's the fourth possible situation when looking for John Harvard? If they're not in the book at all, and indeed, I might get to the very last page and John Harvard's not even on that one, I'd better handle that and say else, like kind of as a catch-all, just quit altogether. And truly, often your Macs, PCs, phones, when they freeze, or again, spinning beach ball or the like, and just weird things happen, that's just because some human made a dumb mistake and they didn't realize that you could somehow get your phone or your laptop into a configuration that they didn't anticipate. So we're going to try to handle that here. Now, this is just one way of writing pseudocode. There's no one way to do this. All of us in this room could come up with slightly different pseudocode, but I think you'll find characteristic are certain building blocks in all of our right answers. Here in yellow are what, as of today, we're going to start calling functions, technically speaking. These are like actions or verbs that literally, in this case, like tell me what to do. Next, we're going to have these things, conditional, sort of forks in the road, so to speak, that take me down this path or another, metaphorically, so I do this thing or something else. But how do I decide if I want to go this way or this way or this way or this way? I need to ask a question. And in programming, we'll typically use what are called Boolean expressions, named after a mathematician, bool. And a Boolean expression is essentially just a question with a yes-no answer, a true or false answer, a 1 or 0 answer. It doesn't matter how you think about it, but it's got two possible answers. And so you can kind of think of these as being expressions with question marks, even though I didn't draw such. Person on page, person earlier in book, person later in book. Those are Boolean expressions, and they just tell me whether I should go down one fork in the road or another. And lastly, there's this. Go back to line 3 in two different places. That represents what we call a loop, like some kind of cycle that's doing something again and again. Now, these are just a few building blocks here, functions, conditionals, Boolean expressions, loops, but you'll find that they're characteristic of so many different languages, one of which we'll look at today, another of which we'll look at next week, and those include, indeed, C and Python and other languages still. And so this is why we focus on these basics and fundamentals in these early days, because we're going to see them again and again. So even if you feel like that fire hose is hitting you sometime, we'll give you today, ultimately, more visuals via which you can hang on to so as to actually write code ultimately in different problems. Now, we'd be remiss in not bringing up sort of what's behind characters like Spot and ChatGPT and other software, artificial intelligence. And it turns out to get to the point of AI, we're actually going to need more building blocks than just functions and loops and conditionals. It's not going to be quite that simple, but this has been a lot so far. Let's go ahead here and take a 5-minute break. And when we resume, we'll take a look not only at AI, but also a specific language called Scratch. So no cake just yet, but we'll come back in 5. Before we dive back in, I just wanted to call out a special guest that we have here today beyond Spot, someone who's come from even farther away. And in fact, if any of you have taken cs50x, the open courseware version of the class, or dabbled in it over the past few years in some of CS50's online social communities, you might have had your questions answered by a certain human from New Zealand. And she's come all this way today to spend this lecture with us. This is CS50's own Brenda Anderson. If you might come up for acknowledgement from all of us here. It's not much, but just a little token of our thanks. Brenda has helped truly thousands of students online for the past many years. And in fact, her own daughter has been the artist behind the duck that's about to loom large in CS50 this year and beyond. So thank you to Brenda. All right, so it's hard to escape a discussion of artificial intelligence nowadays, but we thought we'd use this as an opportunity to connect some of these dots, because indeed, over the course of the semester, we'll not only be talking about artificial intelligence or AI, but really using it all the more constructively to help you solve problems, help you get unblocked when you hit a wall cognitively or syntactically when writing code. And indeed, it's no accident that we have this duck here looming large, which is really the embodiment of the sort of AI that you'll experience within CS50 itself this year. So let's talk about this so-called chatbot that inspired some of those headlines with which we began class that weren't quite on the nose. So the class will still be taught by us humans, but helped by this sort of CS50 duck, a chatbot of sorts. Now, what do I mean by this? Well, it turns out that when it comes to implementing something like an artificial intelligence, we don't quite have all of the building blocks yet, certainly after just today's week 0, to implement something like that, but I think we can sort of skate in that direction intellectually. So for instance, if we were to take a stab at implementing our own chat bot, some interactive text-based program that talks to us and answers questions and the like, we could try borrowing some of today's ideas already, those functions, conditionals, loops, and more, and I could write something like this. If I am writing code or pseudocode for a chatbot, I could program the chatbot to do something like this. If the student says hello to the chatbot, then the chatbot should say hello back. Else, if the student says goodbye, well, the chatbot should say goodbye back. Else, if the student asks how you are, the chatbot should say that it's well. But things get a little harder when you start asking more interesting questions, like, else if the student asks why 111 in binary is 7 in decimal. Now, you could imagine that we just have a conditional with this Boolean expression that programs the chatbot to just give you the answer and explain in an English sentence why that in fact is. But what if you, the student, asks why 110 is 6 in decimal, or why 010 is 2? I mean, you can just imagine the explosion in the amount of code that we would have to write to just anticipate every darn question that you might ask about today and every other class, not to mention all of the knowledge in the universe. So surely there are other ways to implement algorithms that allow something like a chatbot or AI more generally to be fed input still, like all of the internet, all of the World Wide Web, all of the pages and textual content therein, but to let it just figure out how to answer our questions based on those kinds of inputs, assuming the inputs themselves are accurate. So large language models is a term you might have heard bandied about over the past several months, or LLMs. And a large language model really is an implementation in software of code that actually takes as input lots and lots of language, like the text of lots and lots of web pages, dictionaries, encyclopedias, Wikipedias, and the like, and sort of infers from the patterns of English words or any human language what a typical human might actually say when asked a question. And some of these questions are easy, right? Probably on the internet alone, not to mention everyday life, if someone extends their hand and says, "Hi, how are you?" odds are, like with 90% probability, you're going to say, "Good, thanks, how are you?" So I bet we could write software that just infers what it should say probably, statistically, based on those kinds of patterns online. And that's indeed where the world is starting to go when it comes to the most sophisticated of algorithms, where you and I, the humans, we don't try to anticipate every possible input. Rather, we give it a more general purpose input, like all human knowledge, and ideally just let it figure things out. Now, we're not quite there yet, and odds are you've heard of hallucinations or just mistakes that these large language models make, but their inputs are imperfect. And sometimes there's a bit of randomness sprinkled in because you don't want the thing to always say the exact same thing. Even you and I might say, I'm not that great today 10% of the time. So you need to sort of perturb the output in some way. But within CS50, and within this world of large language models, we do have these tools like ChatGPT and Bing Chat and others. And we'll stipulate that for CS50's purposes, the direction we're going this year is that this is what's in the syllabus, ... That it will not be allowed, it will be considered not reasonable to use AI-based software other than CS50's own. So the goal here is not to simply take away tools that are clearly inevitable, in my view, and clearly helpful and productivity savers, but we'd like there to be some guardrails intellectually on just how helpful these chatbots are, because as you've probably seen, if you ask it a question, these chatbots are already pretty good at not just helping you finish your current thought, but it'll hand you your second and your third thought and sort of do the assignment for you. But I think through prompting, so to speak, we'll be able to coax some of our own tools, being computer scientists ourselves, in a direction that you actually find to be the right balance, akin to having a good tutor by your side 24/7 who doesn't just hand you answers, but indeed tries to lead you to the same, so you actually get something out of the experience, and ideally 3+ months from now, those training wheels can come off too, and you're able to still stand on your own. So it will be reasonable to use CS50's own AI-based software, which will actually take the form of a CS50 duck, which is actually available now, and we'll use it throughout the term at cs50.ai, a web-based application that's quite similar to ChatGPT, but that has the personality of a CS50 teaching fellow, or TF, or teaching assistant TA, that also happens to think of itself as a duck. And for reasons we'll get to in a couple of weeks' time, but rubber ducks in particular are kind of a thing in programming. But more on that before long, as you can even see from the one there on my desk. With that said, too, allow me to call out CS50's own Brenda Anderson, whose daughter Sophie kindly not only created the first incarnation digitally of this duck, but also most recently, once it actually did more than quack a random number of times in response to questions, has now been virtually brought to life too. So all that and more over the coming weeks, but you'll find ultimately that the goal is to really bring to life the availability of an AI-based tutor that you have access to, a friend in your next to you, that will help guide you through a lot of the course's challenges along the way. And we've actually rolled it out this past summer already with some of your predecessors through the Harvard Summer School. One student wrote at summer's end that this duck felt like having a personal tutor. I love how AI bots will answer questions without ego and without judgment, generally entertaining even the stupidest of questions without treating them like they're stupid. It has, as one could expect, an inhuman level of patience. So there's actually something really there, because as many teachers as there are in CS50, myself, the course's preceptors, teaching fellows, teaching assistants, and course assistants, there's only so many of us, and we're only awake so many hours of the day. And I think you'll find, too, that we're on the cusp of something pretty remarkable in the coming years, where it's going to get a lot more enabling now to learn material not only within the confines of a class, but on your own ultimately as well. And as one other student put it at summer's end with respect to the duck, love, love, love the duck, we're friends now. So that too awaits. But first, we're going to need to start with the basics. And we started today by talking about binary, and darn it, here it is again. So we can't actually get to the point of using or solving or implementing AI until we understand this. And odds are most of you won't know at a glance what this piece of software does, but these are the zeros and ones that represent perhaps the first program that any programmer writes, which is now a clue to some of you who have dabbled in code before. What does this pattern of zeros and ones tell a typical computer to do? Might someone guess? It's going to have it say hello world, which is one of the very first programs that most any programmer writes. Should you be able to recognize these zeros and ones? Do I recognize these zeros and ones? Like, no, not at all. I just happen to know that they are the same, and that was kind of a leading question. But they are representing data and instructions ultimately. Data like HELLO, comma, WORLD, and an instruction like print that data to the screen. As for what these patterns of zeros and ones are, this is not something that a computer scientist or programmer worries about. We just stipulate that, OK, someone somewhere knows how to do this. And it's probably someone like Intel who makes the hardware inside of the computers. But you and I, 0, can start to view binary more abstractly. We don't care about the zeros and ones. We only care that you can use zeros and ones to represent more useful quantities like numbers and letters, colors, and more. So this, next week, is going to be the code we actually start writing at a keyboard. And this is that language called C. It's the same language I myself learned years ago when taking CS50, when all we learned at the time was C. But this, too, has some crypticness to it. And if you've never programmed before, you can probably wrap your mind around, OK, I'm guessing the printf prints out the hello world. But what's with the semicolon, the quotes, the \n, the curly braces, the hash include, and all of this stupid syntax? A lot of this in the beginning of any class is really a distraction. It is not intellectually interesting, but it's the stupid kind of stuff that's going to trip you up quite often. And so today what we'll do is focus not on syntax, characters on the keyboard, but ideas. Because what really matters in this program is that printf is a function here for our purposes. And that function is to display information on the screen. Everything else, as we'll soon see, has value and will be understood by you before long. But for now, it's a distraction. Let's focus on those building blocks. When it comes time to write code, though, for the curious, especially if you've programmed before, we'll use a very popular free and open source tool called Visual Studio Code, or VS Code. We'll use a cloud-based version of it that we pre-install everything you need in the cloud for you, so you don't have to deal with headaches like getting your Mac or PC to work. You'll use instead this URL, cs50.dev. But more on that in next week, week 1. For now, we'll use another cloud-based editor called Scratch. And odds are some number of you use this probably as early as like middle school or the like. And that was fine to create your own art, animations, games, interactive art, or the like. But we'll use it today for just a bit. And we'll use it in the course's first homework, aka problem set 0, to explore now some of these same ideas. And among the goals today, for the remainder of today, is not to focus so much on Scratch and the particulars, because this is not a language that you're going to use often, but to give you very visual representations of ideas so that when things do escalate next week to C, to the more cryptic, it's the same ideas just typed out instead of dragged and dropped. So by that I mean this. I'm going to go ahead and share in just a moment the user interface of Scratch. But what's nice about Scratch is that this is how we're going to implement that same program today. These are 2 blocks or puzzle pieces on the screen, and they've been interconnected to tell the computer to say hello world on the screen. The user interface that we're about to use will look generally something like this. It's a web-based editor, though you can also download it locally to use offline. And you'll see that on the left here are a whole bunch of puzzle pieces or blocks. They're categorized by color, and the blue ones tend to relate to motion. For instance, the purple ones represent looks. The pink one represents sounds. The yellow one represents events. More on that soon. The orange ones represent control. And then there's operators, variables, my blocks, and even some extensions we can install as well. So it just categorizes things visually and colorfully so that you can sort of find what you're looking for. But we're going to use these puzzle pieces to drag and drop them onto this area here. And we're going to connect them when we want them to do something. What can they do? Well, by default, Scratch comes with this cat here, otherwise known as a sprite, which is a character in a game or in a graphics context. And this cat lives in this 2-dimensional world in which the cat can go up, down, left, right. And you can actually change the cat's costume to be a dog or a bird or anything else. It really is more of an idea than it is a specific animal in this case. But the world that Scratch lives in looks a little something like this. It's like a Cartesian plane with x coordinates and y coordinates. And the numbers don't so much matter fundamentally, except that when you want the cat or any character to go up, down, left, or right by some amount, it's useful to know, for instance, that 0, 0 is the middle, 0, 0 for x, y. All the way up is a y value of 180. All the way down is negative 180. All the way to the left is negative 240. All the way to the right is 240. And generally, you're not going to have to worry about numbers. You're going to use these relatively, go right, go left, go up or down. But that's just the world that Scratch itself lives in here. So let's go about using Scratch here. I'm going to change over to my cloud-based editor here, where I've gone to scratch.mit.edu, and I've clicked Create in order to create a project. And that gives me this blank canvas here. And I'm going to do these somewhat quickly, because I kind of know what I'm looking for. But part of the process with problem set 0 is just going to be clicking and dragging and sort of scrolling around to see what building blocks exist. But I know under events, there's this puzzle piece here, when green flag clicked. Why is that germane? Well, if I zoom out and go back to Scratch's world at the right here, notice that above Scratch's world, there's a green and a red stop sign, which of course is going to mean stop. So if I drag this puzzle piece anywhere into the middle, it's just going to plop where I put it. But what that means semantically is when someone clicks that green flag, I want Scratch, the cat, to do this other thing. Well, what do I want it to do? Well, let me go under looks. And looks here, in purple, have some puzzle pieces like this. Well, I can say hello for some number of seconds, or I can just go ahead and say hello. So let's do that. I'm going to drag this say block. And notice that as soon as I get close enough, it's going to sort of magnetically want to connect. So I can let go, and they snap together automatically because they're the right shape. I don't have to say hello exclamation point. I can change it to the more canonical hello, comma, world. So anything in this white oval is editable that you can change as just text there. If I now zoom out, let me go ahead and click the green flag, and voila, this should be my first program in Scratch. Hello world. Without any of the distractions of syntax or weird characters on the screen, it's just done what I want it to do. All right, let me go ahead and click stop there, and let me make it a little more connected to what we've discussed thus far. So this puzzle piece here, say hello world, represents what type of building block using the vocabulary of today? So it's a function. So these purple blocks are functions, say hello world. And let me give you another piece of terminology. These white ovals that take textual input, in general, those are called parameters or arguments. And they customize the behavior of a function. So a parameter or an argument customizes, modifies the default behavior of a function, like in this case, say. Similarly, in the C code from earlier that we'll see next week, the printf function took a quoted phrase like hello world similarly as input. But more on that in the future. So how does this connect to what the mental model we presented earlier? Well, here's problem solving, as I described it earlier, inputs to outputs with algorithms or code in the middle. Well, what we've got here really is an input of hello world, the white oval. The function or algorithm that it's going into as input is the say block. And what is the output of using this say block, the say function? It's the visual effect of having the cat have the little speech bubble appear above its head saying hello world. So everything we do, in fact, can be mapped back to that very simple idea of inputs and outputs. Well, let's make it a little more interesting, though. It's a little boring to just say hello world all the time. Let me go ahead and drag this away. And if you just drag it to the left and let go, it gets automatically deleted. Let me go under sensing in light blue here. And you'll see there's a bunch of blocks, one of which is an ask block, an ask function, which is going to prompt the human, me, for some input. So let me go ahead and drag that over here. And it snaps together. I could change the question, but I'm OK with that question. We'll use what's your name. But notice that this block, ask, is a little special. It is not just going to display like a speech bubble on the screen. It's actually going to return a value. And this is another term of art today and onward. A return value is some value that can be handed back to you conceptually from a function so that you can do something with it. It's as though the ask function asks someone for their name, writes it down on a piece of paper, and hands you the piece of paper. You can do anything now that you want with that name. And here is how you access the name in this special block called answer, which again, we'll start calling a return value. So if I want to say hello to someone specific, I'm going to do this. Let me zoom out. Let me go back to looks. And let me go back to say. And I'm going to change the say block here to hello, comma. Then I'm going to zoom out. Well, I need two inputs, I think. So all right, I'm going to grab another say block, and I'm going to put it below. And I could just type David, but this is going to defeat the whole point of asking me for the name, and it will only work for me. So I don't want to do that. So let me go back to sensing. And notice the shape is important here. Even if it's not quite the same size, the shape matters. And I can actually drag this and change the input of this say function to be whatever that return value is, that piece of paper that has the person's name on it. And it grows to fill. But now we have a program that I think, when I click the green flag, watch, is going to prompt me, what's your name? And now I have room to type down here. So I'm going to type DAVID. I'm going to hit enter, and it should say, hello, Dave. Wait, Oh, maybe it was, didn't work. DAVID. Here we go. Hello, David. It's missing the hello. But I'm quite sure we have a hello right there. So what explains this bug or mistake? Yeah. Exactly. It's just put another way, my Mac, my PC is just so darn fast that it did exactly what it was supposed to, but it said, hello, David, so fast that we didn't even see, we being the human, the slowest part of the puzzle, see the actual hello. So there's a few different ways to fix this. As you know, we could have it say hello for some number of seconds. So I could kind of do that. So let me do this. I can decouple these by just dragging and letting go so that they're magnetically far apart. Let me go ahead and drag this one, say hello for 2 seconds. I'm going to change the grammar here to be hello, comma again. I'm going to go ahead and disconnect these two. I'm going to throw away the old one that I don't want to use. And I'm going to reconnect this so that now, OK, it's going to say hello for 2 seconds and then my name, hopefully. So let me click stop and start. DAVID, enter. OK, so it's better, but it's kind of like poorly implemented. Like, come on, I just wanted to say hello, comma, David. Why is that hard? Well, maybe we can actually combine these a little differently. And let me propose this. Let me actually get rid of these blocks again. And let me go ahead and just say one thing. But can I somehow combine this to say hello, comma, David, all in one breath? Well, it turns out if I go under operators, I know from having played with this before that there's this puzzle piece down here called join. And it's a circle, or it's an oval. It's a little big, but again, it will grow to fill. And by default, it wants to join 2 words, apple and banana. But whoops, but those are just placeholders. So let me go ahead and drag this over the default hello. Let me change apple to hello, comma, space. And then banana, let me go back to sensing. Let me grab answer and drag and drop that. So now notice that I'm kind of layering my ideas. And put another way, the output of this join block is presumably going to join 2 things together, apple and banana, or hello, comma, David. And then the output of join is going to become the input to say. So aesthetically, it just looks better. It's still correct, but it's just better. So if I type David and hit enter, hello, David. This is what a normal program would presumably do, not show you part of the phrase and then the rest of the phrase. Like, it's just better in this way. So let's connect this now to this same puzzle piece and this methodology. So here's that same puzzle piece. Ask, how do we fit it into this input and output flow with algorithms? Well, the input to that puzzle piece is something like, what's your name? Question mark. Then the algorithm or the code implementation thereof is this ask block and wait. So the human has a moment to type their response in. The output of that function, recall, is a return value. You don't see anything on the screen by default because we've not used say yet, but we get this return value. And let me scooch everything over now so that we can now join those inputs together. So here's this puzzle piece. Let me go ahead and propose that the inputs now to the join block are 2 arguments or 2 parameters, so to speak, hello and answer. They go into that join puzzle piece whose purpose in life is to return 1 joined version thereof. Let me slide this all over logically now so that now that output becomes the input to the say block, and now is why the cat has the speech bubble saying all at once, hello, comma, David. So what we've done here is kind of composed the output and from one function into the input of another. And you can think of this in a couple of different ways, left to right as I did there. We're kind of like stacking these things on top of one another. But at the end of the day, even as programming gets more and more powerful for us, it's just inputs and outputs, inputs and outputs. And thankfully, with built-in functionality from our friends at MIT who designed Scratch, I can even do something playful like this. I can go to that extensions button at the bottom, and there's a lot of fancy things I can add here, like text-to-speech. So let me go ahead and choose text-to-speech. And let me go ahead here and change the say block in purple. Let me get rid of the say block, and let me borrow this. Let me get the speak block like this. And now let me drag and drop this oval. It's going to grow to fill. And I think it's just about to be a little more interesting. Let me click play now. And hopefully this isn't too loud. DAVID, enter.
Hello, David.
OK. Thank you. Thank you. That's a low bar. Let me go ahead and set the voice too. And you might now remember how we began class where we had a robotic computerized voice. Well, we didn't use Scratch at the time, but we could change this in Scratch alone to be a little different. So DAVID.
Hello, David.
Okay, a little creepy, but we can play all day long with that. But the point is that these functions are just now doing something a little different, but it's just these inputs and outputs. Well, let's make the cat more like a cat. Let me go ahead and throw away all of this asking questions stuff. Let me go up to sound, and let me go ahead and drag the play sound meow until done. And here too, it comes with meow. You can add your own sounds,